Okay, let's talk about polyprotic acids. So a polyprotic acid, poly means more than one, protic means proton. It is an acid that has more than one acidic proton. So the acids that we've been dealing with so far have been monoprotic acids. So like HA, this has one acidic proton, so that would be a monoprotic acid. If we had H2A, two hydrogens, it would be a diprotic acid. And if it was something like H3A, it would be a triprotic acid. So the way this works is every time an acid ionizes, it only loses one hydrogen per ionization. So for example, the HA that we've been dealing with has just had a Ka. Just one ionization because there's only one hydrogen to ionize. An H2A, a diprotic acid, would have a Ka1 and then a Ka2, two successive ionizations. An H3A, a triprotic acid, would have a Ka1, a Ka2, and then a Ka3. Three successive ionizations for that triprotic acid. So we are going to do an example of a calculation with a diprotic acid. So this problem says that the diprotic acid, tartaric acid, it says what is the pH of a 0.10 molar solution of tartaric acid, which has the formula H2C 4H4O6. So right here you can see this H2. We are just going to call this H2A for a generic weak acid. We know it's a weak acid because tartaric acid is not one of the 6 strong acids, so it means it's a weak acid. So it means we are going to have to use equilibrium chemistry. So we are doing this, a diprotic acid. There's going to be a Ka1 and a Ka2. There are going to be 2 successive ionizations to calculate the pH. Okay, so it's going to ionize once and then it's going to ionize again. So I'm going to walk us through this. So let's look at, I might just divide the page and we'll say here is the first ionization and here is the second ionization. So the first ionization is going to look like this. H2A aqueous plus water liquid is in equilibrium with H3O plus, that's the conjugate of the water. And now what is the conjugate base of this weak acid going to be? It's going to be HA minus because we're losing one hydrogen. So now we still have one and the charge is -1. So there's the reaction, initial change, equilibrium. The initial concentration is given to us as 0.1, so we don't have any of the products when we start. Minus X plus X plus X, 0.10 minus X, X, X. This is the equilibrium that we're going to use. Also, I forgot to write, the problem gives us the 2 Kas. It says the Ka1 is 9.2 times 10 to the -4th, and it says the Ka2 is 4.3 times 10 to the negative 5. Okay, that was given to us. So here's our first one. We are going to do our first ionization. We are going to use the equilibrium row with the Ka1. We'll say Ka1 equals x times x, so x squared over 0.10 minus x. So let's look at the simplifying assumption to see if we don't have to use the quadratic formula. So the simplifying assumption says if the initial concentration, the ratio of the initial concentration to the Ka, if that number is greater than 5,000, then we can just get rid of that x and assume it is negligible. So I just took the initial concentration, 0.1, divided by the Ka1, 9.2 times 10 to the negative, whoops, I did this wrong, 9.2 times 10 to the negative 4th, and it is 108.69 whatever. This number is less than 500, which means we cannot use the simplifying assumption. It means that x is not negligible. It means that we do have to use the quadratic formula. So I am going to kind of work through the math of this kind of quickly. If you want the work to all of this shown out, I'm happy to do that for you. When I put this in ax squared plus bx plus c form, I get 0, or I'll write it this way, x squared plus 9.2 times 10 to the negative 4th x minus 9.2 times 10 to the negative 5th equals 0. So there's my A, B, C. So now I'm going to use the quadratic formula. X equals negative b plus or minus b squared minus 4ac. And I'm going to end up with two numbers. I'm going to write x equals negative 9.2 times 10 to the negative 4th plus or minus the square root of b squared, 9.2 times 10 to the negative 4th, and I'm going to get two answers. I'm going to get a positive number and a negative number when I solve this. I am going to get that x equals 9.1 times 10 to the negative 3. And I'm going to get x equals negative 1.0 times 10 to the negative 2. So remember what x is. X is a concentration. So x cannot be a negative number. So x cannot be that, which means x is 9.1 times 10 to the negative 3. So at the end of the first ionization, let's just see what the concentrations are at the end of the first ionization. 0.10 minus x, so 0.10 minus 9.1 times 10 to the negative 3 is going to be 9.0 times 10 to the negative 4 molar. The concentration of hydronium at the end of the first ionization is going to be x, 9.1 times 10 to the negative 3 molar. And the concentration of the conjugate base is going to also be x, 9.1 times 10 to the negative 3 molar. This is the end of the first ionization. This is not the end of the problem. And then we're going to go straight to the second ionization. So essentially we're going to do all of this again, but now we have initial concentrations. Let's write that out and see what it looks like. So now what does the second ionization look like? The second ionization is the ionization of this. Now is going to be, this was the first ionization, one hydrogen left. Now the second hydrogen is going to leave. So now my reactant is going to be this HA minus. Now this is my weak acid, aqueous. plus the conjugate base of this, which is now going to be A2 minus. So now this is my second ionization. This is my second removal of the second hydrogen ion. Here was the first, here is the second. So that's my reaction. So now I do have an initial concentration of this HA right here. It's 9.1 times 10 to the negative third. I also have an initial concentration of my hydronium ion, 9.1 times 10 to the negative third. I do not have an initial concentration of this conjugate base. And again, the water is not included. So now it's going to be minus x plus x plus x, 9.1 times 10 to the negative third minus x, 9.1 times 10 to the negative third plus x, and then x. So now I'm going to use the Ka2 to solve here. So it's going to be Ka2 equals 9.1 times 10 to the negative third plus x times x over 9.1 times 10 to the negative third minus x. So now if we use the simplifying assumption and we look at the initial concentration, 0.1 divided by Ka2, 4.3 times 10 to the negative 5, it is a bigger number than 500. It's 2,325. So now I can assume that x is negligible, which I don't even really need to do because this minus x and plus x, this is just going to factor out. So when I write this, I'm going to say Ka2, which is 4.3 times 10 to the negative 5, equals 9.1 times 10 to the negative 3 x over 9.1 times 10 to the negative 3. So 9.1 times 10 to the negative 3 will cancel. I get x equals 4.3 times 10 to the negative 5. So that's x. The question is asking for the pH. What is the pH? So this is x. Remember, I want pH, so I want what is the hydronium ion concentration. Well, the hydronium ion concentration is 9.1 times 10 to the negative 3 plus x, which is 4.3 times 10 to the negative 5. Let's see what that is. 9.1 times 10 to the negative 3 plus 4.3 times 10 to the negative 5. I think it's too small to even make a difference. With two significant figures, yes, the hydronium ion concentration is still, even after this change, 9.1 times 10 to the negative 3 molar. So now once we have the hydronium ion concentration after the second ionization, this is what we're going to use to solve for the pH. So we'll say pH equals the negative log of the hydronium ion concentration after both ionizations, which is this, 9.1 times 10 to the negative third. It's two significant figures, so my pH should have two decimal places. Negative log of 9.1 times 10 to the negative third. pH equals 2.04. So that is the pH of this diprotic acid. So the key to this are the successive ionizations. So this is the first ionization. H2A is going to lose one hydrogen and become HA minus. The second ionization, what you ended with as a product in your first ionization, becomes a reactant as your second ionization. HA minus is going to lose this hydrogen and it becomes A2 minus. So here's an example of a polyprotic acid, weak acid ionization using successive ionizations, Ka1 and Ka2, to solve for the final hydronium ion concentration, to use that to solve for the pH.